So when we do calculations, we should not be gaining or losing precision. So our results have to reflect the precision of the measurements that we started with. So that's why we look at the significant figures. Two broad categories of operations, multiplication and division, are similar, just opposites of each other, and then adding and subtracting. So there's a different rule for each. So in multiplying and dividing, the result that you get should have the same number of significant figures as the factor, the number you started with, that has the fewest significant figures. So multiplying and dividing, we're looking at sig figs. Okay, how many sig figs? So the examples here, we're multiplying these numbers and our calculator is going to show us something like this. What we want to do is we want to look at how many sig figs does each of these numbers have. So this one has 4, and this one has 5, and this one only has 2, because the leading 0 doesn't count. So the smallest, the fewest number of sig figs is 2, and so that's how many sig figs our answer should have. And so we take what the calculator gave us, and we're going to round it so it only has 2 significant figures. Here's another example, one number divided by another. Do it on the calculator, write down what the calculator shows you, then look for sig figs. So here I've got 5 significant figures, and over here I've got 3. That means my answer can only have 3 significant figures. So leading 0 doesn't count. I count 626. Those are 3 digits, and I'm going to round it there. Any questions? Adding and subtracting, the result has the same number of decimal places as the quantity with the fewest decimal places. So here we're counting decimal places. Multiplying, dividing, count sig figs. Adding and subtracting, you count decimal places. So there are several different ways you can think about this, and I'll show you one here, and then in lab, if you want, I can show you some other ways to think about it. Just need to find the one that clicks with your brain, and then it'll be easy. So we can stack the numbers up as if we were going to do the math without a calculator. Use your calculator, right? Practice your mental math somewhere else. Just use the calculator. So use the calculator and figure out what the answer is supposed to be. When you pretend you're going to do this by hand, you have to line up all the decimal places, right? And so then what you're going to do is you're going to look at the numbers and find out which one ends in the largest place. So as we're going left to right, this middle number ends sooner. And so draw a line to the right of that. Over here we've got 5.9 minus 0.221. This first number ends after the first decimal place. And so I'm drawing a line all the way. And that's going to tell you where your answer should end. How does that work with number of decimal places? Well, if I look at these numbers, this one has 3 decimal places. This middle one, come on pointer, has 2 decimal places, and this one has 4 decimal places, which is the fewest. 2 decimal places. So my answer should have 2 decimal places. And the line method gives me that same result. Yeah. Yes, if there was a whole number, it depends on whether it's just a whole number measurement or whether it's an exact number. If it was an exact number, it's not going to affect it at all. If we had like 7 in here, then we'd have to draw the line over here. And then when you're multiplying and dividing, you have to, with adding and subtracting, you have to consider the operations separately.
So for this, does the result have the same number of significant figures as the factor with the fewest decimal places, or do you just do the fewest number of decimal places?
The answer has the same number of decimal places as the factor with fewest decimal places.
So you could have a factor that has a different number of significant figures, and then your result will just be the same number of decimal places.
Right. So in adding and subtracting, you can end up with way more significant figures or way fewer significant figures than any of the numbers that you started with. It's all to do with the decimal places. And if that bothers you, I can show you why it is. So rounding. When you're rounding, you just look at the first digit you're going to get rid of. If it's 5 or greater, you round up. If it's 4 or less, you round down. Okay? It's very important that when you round numbers, you don't change the overall size, the magnitude of the number. So, an example here. $24,938.99. We're instructed to round this to 3 significant figures. So, I'm going to start on the left, and the 2 is significant, and the 4 is significant, and the 9 is the third significant figure. I'm going to look at the next digit to see, do I round up or down? I round down, right? So 2, 4, 9. Can I round 24,938.99 to 249? No. When you round a number, you just go to the nearest something. You don't change the magnitude, right? It's still really close to what it was before. So here I am rounding in the thousands place. Well, no, hundreds place. Hundreds place, right? So anytime you're rounding in the tens, hundreds, thousands, whatever, you need to be careful because people do dumb things, and they'll round 24,000 to 249. How do I fix that? Well, I would need to put place-holding zeros in until I got to that decimal point. I don't want to write the decimal point because that would imply that those zeros are significant when they're not. But I have to put in placeholder zeros. Because now 24,900, that's close to 24,938.99. The best thing to do in this situation is to put the number in scientific notation. If you put it in scientific notation, you cannot make this mistake. And I can put it in scientific notation and round it all at once. So I want to round this to 2 significant figures. So I've got 2, and my decimal point goes next, and then 4 and 9. So there's my 3 significant figures. I look at the next one. I don't need to round up, so I'm all good. And now I've got times 10 to that. Let's just get those out of the way. So I move the decimal place 1, 2, 3, 4. 4 places. So my exponent is a 4. Positive or negative? Positive. I'd feel really good about that as a monthly salary. Ooh, that'd be sweet. And then the unit looks a little weird in scientific notation, but for dollars, the unit goes in the front. So 2.49 times 10 to the 4th. The times 10 to the 4th preserves the overall size. It takes the place of those placeholder zeros. Yes?
So you don't put a decimal point at the end of the 900, but if you did it in scientific notation, you put a decimal point on it?
Okay, so when I wrote it this way, come on, pointer. There. When I wrote it this way, I didn't put a decimal point here. So rounding here, this slide is mostly a waste of time. I'm just going to drop down to this one. We're rounding all of these to 2 significant figures. So here, I'm going to keep the 5 and the 3. And then I look at just the next digit. You don't want to go all the way to the end and round up and down backwards. That's a lot of work, and it'll sometimes give you the wrong answer. You just look at the first digit you're going to drop, round up or down. So because the next digit is 4, I don't care about the 9. Because this is a 4, it rounds down, and I just call that 5.3. So we kind of hinted at this earlier. To avoid rounding errors in multi-step calculations, round only the final answer. Do not round intermediate steps. you can introduce error doing that. Sometimes we have to write down intermediate values. Sometimes we do a calculation and we don't even recognize that we're going to need to use that number later in another calculation. And so I'm going to show you how to take care of that. What we want to do is we want to keep track of the sig figs in those intermediate numbers without rounding them. And we can do that by underlining the last significant figure. My recommendation is carry at least 2 digits beyond the underlined. You can carry all of them if you want to, and some of you will, and that's fine. I think it's tedious writing down all those numbers. But carry at least 2. If you carry 2 extras, you're fine. Too many digits is better than not enough. So when we do a calculation, and like these examples are showing us, the first answer we write down has too many digits. It should have at least 2 extra digits, even if we're not going to use it for anything else. And then we round for our final answer. So in this example, we've got mixed multiplying and subtracting. So we would do this subtraction first because it's in the parentheses. And when I subtract these 2 numbers, my calculator gives me 0.479. I'm going to apply the rules for subtracting the fewest number of decimal places. This number has 3 decimal places. This one has 2 decimal places. So the result of that subtraction should have 2 decimal places. So I underlined the 7. If that was all I was doing, I'd round it to 0.48. But I'm not done yet. So I underline the 7 and I let the 9 hang around. When I look at this number, though, I recognize that the sig figs stop here. So how many significant figures am I indicating in that number? Just 2. The 4 and the 7. The 9 is there, but it's not counting as a sig fig. So this has 2 sig figs. And then I'm multiplying by these other numbers, 3 sig figs and 4 sig figs. 2 sig figs is the fewest number. So I wrote down what the calculator says, and then I'm rounding to 2 sig figs. And so it gets rounded to 19. Any questions? You'll get some practice with this on the worksheets. And we'll do some practicing right now. So this first example, it says perform each calculation to the correct number of significant figures. That first one is multiplying and dividing. So we don't have to write down any intermediate results. We can just do the calculation. 3.10007 times 9.441 times 0.0301 divided by 2.313. And my calculator's giving me a big old mess. I like to think of it as being efficient rather than lazy. I would rather not write down all of those numbers. So before I write down my unrounded number, I'm going to look at what I've got there, and I can figure out how many significant figures am I going to round to. Which of them has the fewest number of significant figures? The 0.0301, right? It only has 3. So my answer is going to get rounded to 3 significant figures. So what I'm going to do here is I'm going to write down 3 significant figures and then the next 2 digits. So 0.380, and I'm going to underline that to remind myself that's where my last significant figure is. And then I'm going to write down the next 2 digits. By keeping 2 digits, you don't even have to think about rounding up or down. It doesn't matter. Just write them down. If you want to write all of them, go ahead. Nothing wrong with it. I just don't like doing it. Now I'm going to round. I see there's a 0 there. The next digit is an 8, meaning I have to round up. And so this should be 0.381. An advantage of doing this is if I realize I got the wrong number of significant figures, I might be able to correct that without redoing the problem. But perhaps more importantly, I might find out in half an hour that I need this number in another calculation. I don't want to use the rounded version. I want to use one that has at least 2 extra digits. And so I can just pick this one and use it in my next calculation. So that's what I recommend that you do. Okay, let's do letter B. So adding and subtracting, both using the same rule. So again, just do it on your calculator. It is important to understand order of operations, but it's also important not to lose your mind over that, okay? PEMDAS, right? Addition, subtraction in there. Okay, when you have, it's addition and subtraction. Here we have addition and subtraction. We're not going to do anything funky like do the subtraction first and then do the adding or anything like that. Just start at the left and go across to the right, and your calculator will do it for you. Okay, so don't overthink those things. 0.881 plus 132.1 minus 12.02. So I can write down everything, and this time it's like, well, there's not that many digits, so sometimes I will just write down all of it. 120.961. Looking at my numbers, adding and subtracting, I'm looking for the number with the fewest decimal places. It's important when you're doing that to have your numbers in decimal notation, or if you have to use scientific notation, all the exponents have to be the same. Otherwise, you can't compare decimal places. And there's a problem on the worksheet that'll make you do that. These are all decimal. So I have 3 decimal places and 1 decimal place and 2 decimal places. That means I'm going to round my answer to 1 decimal place. So I'm going to underline that to remind myself that's my last significant figure. And then I'm going to round. So I look at the next digit, it's a 6, I have to round up. That makes the 9. So the 6, I have to round the 9 up to a 0, to 10, which rounds the next one up, sort of like, you know, when you're watching the odometer on your car, and it just, like, all the things flip over. So 1, 2, 1, I still need 1 decimal place. And so it's very important to put that 0.0 there. We don't want to just lose that, because I was rounding this number to have 1 decimal place. I need to have 1 decimal place when I'm done, even if it ends in a 0. Sometimes it does, and that's okay. Okay, this next one, I've got multiplying, dividing, and adding. I'm going to do the adding first because it's in parentheses. So 44.11 plus 1.223 equals. And I'm going to write this down so I can keep track of things. That's 45.333. That was adding. I'm comparing number of decimal places. How many decimal places should 45.333 have? It should have 2, because this one has 2 decimal places and that one has 3. So if I was done, I would round to 2 decimal places. How many significant figures am I trying to indicate when I write that number? I'm trying to indicate that there's 4. The underlined digit is the last significant figure. I'm letting the other 3 hang around so I don't have rounding errors. Now I've got this number times this number divided by this number, and I'll do the math. 2.511 times 21.20, if you want, divided by 45.333. And I'm getting a mess. So I have multiplying and dividing, those use the same rule. The factor with the fewest significant figures. So this one has 5 significant figures, this one has 4 significant figures, and this one I am trying to represent that has 4 significant figures. So my answer should have 4 significant figures. So I'm going to write down the first 4 digits, 1.174, and I'm going to underline that 4th one to remind myself, come back and round it there, and then I'm going to write down the next 2 digits, 27. Now I can round, and this is going to round to 1.174. If I need to use this number in a calculation later, I can use this much less rounded one, and I won't have any errors from rounding. Letter D, here we've got multiplying and adding, and we're going to do the parentheses first. So I'm going to multiply these 2 numbers, 12.01 times 0.3. And I'm going to write this down. It's possible to do it without writing it down, but it's going to take a little bit of practice. So for now, just write it down. That's the multiplying. Multiplying uses count the fewest sig figs. Well, this one has 4 sig figs, and this number only has 1 significant figure. So the result of this multiplication can only have 1 significant figure. That's the first digit. That's the fewest number of significant figures you can have. If you're rounding and it looks like you're rounding to 0 significant figures, you're counting leading zeros, and that's what's screwing things up. You're always going to have at least 1 sig fig. So I'm going to take this number and add it, but I underlined the ones place. For significant figure purposes, this has no decimal places. It ends in the ones place. So when I add it to this number, my answer has to end in the ones place. So I've got the 3.603 plus 4.811. My calculator says 8.414. But the sig fig rules tell me I have to round that to the ones place. And so I'm going to report this as 8. Yes?
How do you know which rule to use for this multiplication?
So how do you know which rule to use? You're going to look at the specific operation that you're doing. So you have to do the multiplication separately from the subtracting. And so you'll have to look at an intermediate result and use the rule for that one. If you're multiplying, use the multiplying rule. If you're adding, use the adding rule. And then you take that one with the other, and now I'm using adding, and so I'm going to use the adding rule. So we're breaking it into individual pieces.
So, since we multiplied then added, why did we just add division?
Because the result of this multiplication would only have 1 significant figure. So it's tempting sometimes to round, and that would round to 4. And then 4 plus 4.811 would give me 8.811, which would round to 9, which is not the same.
So, for adding purposes, you keep it the same, but since it doesn't have any decimals after, that's why it's a whole number?
Right. This is indicating the last significant figure. So this number I'm trying to indicate has 0 decimal places. And so these are here. I'm going to let them hang around still, but they don't count as significant figures. So it's like it only has this digit here for sig fig reasons. Okay? And it's one of those things, it's a little bit like learning how to play Dungeons and Dragons or something, or even a simple board game, or a card game like Exploding Kittens. Have you played Exploding Kittens? It's really kind of disturbing. You can read the rules, and it's like reading a chemistry book, right? It just doesn't really make a whole lot of sense. How do you learn how to play the game? Well, you start playing, right? And you consult the rules when you aren't sure, and it's a lot easier if you play with someone else who knows. Because then when you play the wrong kind of card, they'll say, no, you can't do that. Well, why can't I? Well, this rule. And you learn the rules as you make mistakes and you get corrected. This is something that in order to be good at this, You have to play the game, make mistakes, get corrections, and then it'll become clear. Once you know how to play a game, the directions, the instructions make sense. But when you've never played it before, you just can't get your mind around it. So I'm teaching you a game. It's just not very fun.
Is there ever a time where you do like just a basic calculation, like a multiplication or a division, and the amount of significant figures that you're required to have, you don't have in your...
That's a good question. That's an excellent question. So I think what you're asking is, you do the calculation, and you're supposed to have 3 significant figures, but your calculator is just showing you 2 digits.
Right.
So
Like it gives you like a larger number, so like 1,000, but like you need like 3 significant figures.
okay, so what can happen is, you might end up with like 1.5. But sig fig rules say I'm supposed to have 3 significant figures. Well, your calculator doesn't understand significant figures. It came out to 1.5. Your calculator's saying the next digit's a 0, dummy. I don't need to show you all those zeros. So then we have to be smarter than the calculator. And if I need 3 significant figures, I'm going to put the 0 in there. It can also happen that you could end up with a number like 10,000. If I put a decimal point there, then all the zeros are significant. If I leave the decimal off, none of them are. And my calculation is telling me I need 2 significant figures. Well, I could underline this, but the reader might not understand that. Scientific notation. So I need to put that one in scientific notation, because in scientific notation, I can specify how many of the zeros are significant. So 1.0 times 10 to the 4th, I can write 10,000 with 2 sig figs. Good question. Anybody else? Precision and accuracy. These are similar concepts, and yet there's a significant difference. Accuracy is how close to the true value is your measurement. Precision is how close to each other are a series of measurements. Okay, so here we have an example of 3 different students weighing a block of lead with a true mass of 10.00 grams. Some of them are good at this and some of them are not so good at this. And so we can show a table, which is how we would typically record data in the lab. You just write down the numbers. And then they've calculated an average of their values. It's hard to look at this and see what's going on. And so that's why we often graph things, so we can graph this data. And there's a section at the end of the book. I'm not going to cover it in lecture, but I encourage you to read it. It's about how to read graphs, because we will have a lot of graphs, but I just don't have time to go over it in class. So here, student A. So here are each of the masses that they recorded. So the mass is on the y-axis, and just trial number, it's a bar graph, so we can see all 4 of them. And we see this one is high and this one is low, and these are in between. There's a lot of variation here. They're all over the place. That's not precise. Those are not close together. This student's values are all really close to each other. Those are precise. These are close to each other. Those are precise. So this is like if you're throwing darts at a dartboard. Every time you throw the dart, it lands very close to the other darts. It may or may not be on the center, right? You can be precise and off. How do we determine accuracy? Accuracy is how close is the value to the true value. So we take multiple measurements like this and average them. The average here is 10.13 grams. This is the true mass, 10.00. 10.00, the uncertainty is in the second decimal place. So the value that I come up with here should agree up to the second decimal place. There might be a little bit of difference in the second decimal place, but this one is not. This isn't good. They've got variation in the first decimal place. This is not accurate. It's not precise. Student A sucks at weighing lead blocks. Okay, so here we have student B. Student B is precise, but we look at the average here. Don't know what happened for this person, but their average is too low. They were precise, but inaccurate. Really good at getting the same measurement, but it's wrong. So that's not good either. And then we have student C who nailed it, good precision and good accuracy. So here the average 10.01. The uncertainty is in the last recorded digit. So 10.01, uncertainty in that place, agrees with 10.00, right? Because the uncertainty is in the last digit. The difference is in the last digit, so those are considered to be the same. So student C is good. It is possible to have an accurate result with poor precision as well. You've got scatter all over the place, but your average is right on. That's better than being precise and inaccurate. So, precision and accuracy are affected by two different kinds of error. Random error, as its name suggests, is random. Has an equal chance of giving you a result that's too high or too low. So one way to get around random error is taking multiple measurements. Because the first measurement might be too high, the second one might be too low. When you average them, the random error will cancel out. And that's why you'll see in lab, we often measure things or repeat an experiment 3 or 4 times so that we can get rid of random errors. Systematic error tends to be either too high or too low, and that will affect the accuracy of your result. So, if you're going to the butcher shop and buying deli meat or something, and the clerk keeps putting his thumb on the scale, then the mass is going to read higher, and you're going to get cheated, right? Because you're going to pay more for the meat because the guy's putting his thumb on it. If you read a graduated cylinder incorrectly, you done? I have these conversations at the trains. What was I talking about? Graduated cylinder, thank you. Graduated cylinder, you're supposed to read the bottom of the meniscus. If you read the top of the meniscus, your volume's always going to be too high. That's a systematic error. So systematic error can come from user error, you're using the device incorrectly, or it can come from a poor instrument, badly calibrated or not functioning correctly.